Welcome everyone, thanks for coming the first seminar of 2024. By the way, Happy New Year. It's great that we have Dr. Jae Sung Yun from University of Surrey, UK. I think most of the people in this room know Jae very well. He has been studied and worked in Surrey for more than 10 years, 12 years you just mentioned.
Yeah.
He's now a lecturer at the University of Surrey, UK, and also a adjunct lecturer at Surrey. So during his research, he mainly working on advancing the thin film photovoltaics using the scan probe microscopy. Today he will talk about progress in thin film photovoltaics from nanoscale innovation to device efficiency. So let's welcome Dr. Jae and the stage is yours.
Thank you.
Thank you.
Thank you, Kaiwan, for kind introduction. So as Kaiwan mentioned, I have been here for over 12 years, and it's been now 2 years since I moved to the UK, and I'm glad to be back here in this nice weather. So today I'm going to talk about progress in thin film photovoltaics from nanoscale innovation to device efficiency. So I just wanted to give a brief introduction to my institute. It's a campus located in near London, I think. It's around like southern part of the London. So you can take a fast train, which only takes like 35 minutes to London Waterloo Station. So it's quite close to London. And our campus is actually the first campus which try to achieve net zero campus by 2030. So there will be around 12 megawatt of PV installed by 2030. Which our university is located in a town called Guildford, which is very nice town. I hope everyone, whoever comes to the UK, come and visit me. I can show you around. It's a sort of a historic town in the UK. A university has around 17,000 students, and we have a very good research center, including Surrey Space Center, and also they're doing very good research. They're doing very good research in telecommunications. So this seminar has three main parts: structural defects in solar cells, perovskite solar cells, and wideband gap perovskite. So I will mainly talk about perovskite thin film, and hopefully we could have some more understandings in perovskite solar cells. So part one, thin film. So I think many are familiar with the silicon solar cell process. The wafer, fabricating wafer, is a sort of an energy intensive process, which has a good efficiency, good stability, currently dominating the market. Whereas thin film solar cell, the fabrication process is known to be much straightforward, has a low material consumption. It can be deposited onto a flexible substrate, and there are also low temperature processability, and we can make a very large monolithic integration devices. So that's advantages of the thin film. However, if you do see this market dominance, the wafer-based solar cells have more than 90% of the market dominance. Whereas you can see that thin films, the market dominance is gradually reducing. It's more like less than 10% in the current market. And most of them are cadmium telluride manufactured at First Solar. So what has driven the cost reduction of wafer, and that actually make the thin film step out of the market? I think the main driver is related to the cost of the wafer. So wafer processing cost back in 2010, where aluminum-based backsurface filled solar cells, the cost of the wafer processing and silicon was around 45%. You can see it gradually reduces, and nowadays with a PERC it's actually less than 10%. So you can see that has been great reduction in terms of the cost of dealing with silicon, including the low material of the silicon. So it's completely gone very cheap, and now the efficiency has gone up, so which makes a very competitive PV technology. And this is the PV cost history. So manufacturing cost, you can see that it was actually over $1.5 per watt back in 2010, and now it's below 10 cents per watt. And this is the point where I started my PhD, and I started working on thin film photovoltaics, where the cost was quite low compared to the silicon wafer-based solar cells. So actually, since I started my PhD, you can see that there has been great drops in terms of the cost of those silicon solar cells. So back then, I started working on crystalline silicon thin film on glass. This technology is not much interest in these days, and we have been working hard to push the efficiency. So it's actually, the concept was to sort of propose that we can make a thinner and cheaper silicon wafer that is can be deposited onto the glass substrate. So you can see that the efficiency has gone up to around 12% by the time 2013. But as you've seen in the previous slide, the cost of the silicon solar cell have gone down much. So unfortunately, at 2013, the place where we fabricate our thin film solar cell had closed. So that's the last photo of our the facility. So we had a little closing ceremony. I think some of you, including Jae Sung Yun, we were there for quite long to boost the efficiency, but eventually it sort of lost its competitiveness in thin film market. But I did learn quite a lot during my PhD, where I could study the microstructural effect. For instance, this is the silicon thin film on glass, and we fabricate crystalline silicon film using the laser crystalline process. So we scan the laser to crystallize and fabricate high quality silicon thin film, and there was definitely some structural effects, such as you can see the crystal orientations. So this PL spot here, which has a very high intensity of the PL, you can see that they have 100 grain. So I took this sample to EBSD and checked why this spot has very high PL intensity, and we found that there is actually a grain orientation dependence, which actually changes the lifetime of the carriers. Also, if you have a random crystal orientation, it gave us a bad performance and bad carrier lifetime. My colleague Jae Sung Yun has done very nice work on finding out what the problem is with this crystalline silicon thin film, and there happen to be a lot of dislocations within the grain. So you can see that this is a TEM image. You can see a lot of defects, intragrain defects inside the crystal grains. Also, I have found out that there are a lot of twin boundaries if you scan, if you crystallize your materials, and with a laser crystallization method. And there were a lot of sigma 3 CSL boundaries, and try to investigate what their impact is on the performance. So I've learned that nanoscale defects play a very important role in polycrystalline materials. And then I moved on to Halide perovskites. So the material is still polycrystalline, as you can see from image here. It's got around 500 nanometer thick absorber. It's got very high absorption coefficient, especially in the visible wavelength regions, and it's got very high carrier lifetime compared to other thin film technology, and it's a direct bandgap material. So if you see the progress of the Halide perovskite solar cells, it evolves quite fast. So Back in 2012, it was around 12%, and now it reached around 26%. Also, there has been large interest in tandem solar cells, silicon perovskite tandem solar cells. Now it reached, so this is old data, it's now over 34%. So Halide perovskite, we have a ABX3 crystal structure. A site, we have an organic cation, and which is sitting in the middle here, and the B side is usually lead. It's hard to replace actually lead with other non-toxic material. So there is going to be always a lead with a high efficiency perovskite material. And this lead is surrounded by halide ions such as iodine or bromide, which has an octahedral structure. So you can see that we can combine many different compositions. So we can have methyl ammonium as organic cation, lead and iodine, or we can even have a bromide, and we can mix them as you like. But they will give you a different morphology, different crystal structure, and different band gap. A good thing about halide perovskite, which is known to be defect tolerant. So when I have seen this material first, you can see that there's obviously a lot of grain boundaries. Grain size is around 500 nanometers, and nowadays the highest efficiency devices still has a lot of grain boundaries. People are reporting that this material is defect tolerant. So if you see the defect density, which is around 10 to 15, up to 10 to 16. So if you compare it with silicon solar cells, it's very hard to understand why such defective material can perform such high performance. So it's good to sort of study what these defects do in terms of performance. So another point I wanted to make is that perovskite solar cells, which is a band gap tunable material, so you can change your material band gap by having different composition. So I think people are familiar with tandem concept, where we can put high band gap material on top of silicon. So we can have a band gap around 1.6 to 1.8 eV. So we can collect a wider spectrum of the light. And there has been a lot of great progress. So now people are able to deposit a perovskite layer conformally on top of the silicon, textured silicon surface as well. So as I mentioned, you can tune the band gap of perovskites. To do this, we need to change the composition of the halides. So if you see, this is methyl ammonium lead perovskite, and if you have iodine only, which is this one, the band gap is around 1.6, so slightly less than 1.6, and you can gradually increase the band gap by putting more bromide into your material. So you can see that you can put around 0.2 to 0.5 bromide, and you can tune the band gap around 1.65 to 1.9, where we can have the optimum band gap for tandem perovskites. However, if you put more bromide, which means if you increase your band gap, you will actually have a lot of losses in voltage, and people are reporting that there are maybe interfacial losses in these wide band gap perovskites. So if you see record efficiency of perovskite material, perovskite solar cells, they are mostly a narrow band gap, which we call around 1.55 to 1.6 eV. So that's the where the high performance perovskite solar cell is, and there are many issues related to wide band gap perovskite, which I will introduce later. So what happens in this wide band gap perovskite, if you put iodine and bromide in order to enlarge the band gap? So ideally, we can think about having a very nice mixture of the halides. That happens in dark, so iodine and bromides are just uniformly distributed under the dark. However, under the light illumination, these halide ions, they segregate. So there's iodine segregate regions and bromide segregate regions. So ultimately what happens is that if you measure PL, this is the original PL signal, you can see that as you continuously illuminate light, you evolve two peaks of the PL. So there is the iodine peak, iodine rich peak, and there is a bromide rich peak. So you will eventually have around 1.6 eV narrow band gap and wider band gap regions formed in your material, and there are going to be a carrier funneling. So the electrons just move to the narrow band gap where it is supposed to create voltage. So as I mentioned, the perovskite cells have a very good efficiency when it's in narrow band gap. So the efficiency deficit is quite small. If you see around 1.55 eV perovskite. However, when perovskite has a large band gap for tandem purpose, the current status of the efficiency is only around 20%. So there are actually a lot of gap, a lot of deficiency. So we need to work on further in order to improve the efficiency of the wide band gap perovskite. And I think this is sort of a hot topic now for people who are interested in tandem devices. So what happens when you mix iodine and bromide? So people report that the formation energy of these materials are different. So if you mix them, you will eventually have sort of quite inhomogeneous or uneven crystal structure formation. So there's a structural growth difference which can be due to the solubility difference between these two halides. So there are going to be some precipitation, and there is also difference between iodine and bromide. And the main reason that these ions are moving around and segregate is that their diffusivity is so high, and they just try to aggregate in nanoscale clusters. So I have happened to work with a collaborator in Korea University, and we try to understand what happens in terms of microstructure for these wide bandgap perovskites. So we fabricated some wide bandgap perovskite, various wide bandgap perovskites from 1.55 eV, so these are narrow ones, and we made around 1.75 eV and 1.9 and 2.3. So we changed the bromide ratio, increase the bromide content. So if you can see, the Fourier deficit is definitely higher as you enlarge the band gap. The microstructure wise, we took these materials for AFM analysis, and you can see when the band gap, when we put 5% of bromide, this is how the topology looks like. The grain size slightly reduces when we put a bit more of bromide, 15%. And there isn't much difference between these two when we put 30% of bromide, and we can see that even grain sizes get larger when we put 50% of bromide, which gives us around 1.9 EV. So we measured Kelvin force microscopy, which measures the work function distribution of your material. And interestingly, what we observe is that unlike the grain shapes and grain size are sort of comparable, we can see that there are regions where they have a very high work function. So you can see that some of the grains in here have different work function compared to the other area. And these sort of abnormal grains, number of abnormal grains increases if we put more bromide into your material. So, and that sort of saturates at 30%, and we see a stronger, very large contrast between the grains, which means that there are a very high, huge difference between work functions. So there is clearly a very inhomogeneous distribution of your grain from the beginning. So this is measured under the dark, and we can see that there is a very non-uniform structural homogeneity. So, and these grains with a different work function, they happen to have a very different morphology. So if you see this AFM image, these grains are sort of very flat and kind of embedded inside into the film depth. And the height, if you see the height profile, the regular grain has like a valley shape. It's a very typical structure of a grain in perovskite, whereas these abnormal grains are having a flat, a very flat nature in the middle. So we measured KPFM under the illumination in order to see what these grains are in terms of their band gap nature. So we can illuminate two different wavelengths. As I explained earlier, we can have different band gaps in your materials for wide band gap perovskite. So under the light illumination, they will have bromide-rich region and iodine-rich region due to the phase segregation. So if you illuminate blue light, larger energy light, you can see that we can see more responses in bromide-rich grains, and if you use around red region, we can make the iodine-rich region more responsive to the KPFM signal. So this is measured in under the dark, and you can see those grains are the abnormal grains. And if you illuminate, say 720 nanometers, so lower band gap, actually large low band gap material wavelengths, you can see that these regions become brighter. So these dark regions where the abnormal grain is more responsive to this iodine-rich 1.6 eV relevant wavelengths. So these flat grains, we think that they are only responsive to 720 nanometers. So we think that these are probably the narrow bandgap regions compared to the other regions. Also, we can perform nano IR and HIM SIMS in order to probe microstructural composition homogeneity. So that's the topography, and we can probe lead and iodine, and we can also probe the A site as well. So these grains with a flat grains have a higher signal in lead and iodines. You can see from here. And also we have more methyl ammonium. So that's the abnormal grain in here. So that's the one. And we can see that they have more methyl ammonium compared to the Fa, this other A-site cation. And also we probe the TEM. So we try to measure if these grains are only happening, if such composition inhomogeneity only happens on the surface. So we check the cross-sectional and perform the EDX and found out that these grains are actually not just only like the grain surface, but within entire film thickness. So we found out that these grains are lead and iodine rich, and as well as methyl ammonium. Just to note to you that we have a nano-IR capability. So this figure, these results are obtained from Oak Ridge National Lab in the US before, so where we can probe the nanoscale nanostructure using nano-IR. But now we have this instrument in here in the School of Material Science, and I'm collaborating with Professor Jan Seder in School of Materials, and you can contact me or Minu Munyong. They are all around to discuss you with measurement for your materials if you're interested. Also, we put more bromide, up to 15% bromide. There isn't much hysteresis. So in Halide perovskite, you can see some of the samples having IV hysteresis. And this hysteresis appears when you put 30% of the bromide. So if you have a wide band gap, you obviously have a large hysteresis due to the ion migration. So this is also linked with phase segregation. So if we measure KPFM under the dark, and we continuously measure. So each map takes around 4 minutes, and we measure along the dark and light illumination. So we measure the same region, and we turn on the light at this point, and we turn off the light. You can clearly see that before the measurement, before the light illumination and after illumination is very different. So that's the before illumination, where you can see that this the flat grain region is confined within the grain, and after the illumination they sort of spreads out. So we think that these mobile ions, so halide ions, are sort of spreads around the grains and even across the grain boundaries. That's why we have a very bad hysteresis in your material before and light illumination and during the illumination as well. So I'm going to keep talk about wide bandgap perovskites, and one of our students, Nur Sultan, has done very interesting studies on wide bandgap perovskites. So as you know, when solar cells operates, it will have a higher temperature than obviously 25 degrees. So what will happen under higher temperature, say 80 degrees for wide bandgap perovskites? So there happen to be some reports on the suppression of the phase segregation on the high temperature, and Nur Sultan has done some PL measurements. So if you see, that's the 30% bromide material and with a band gap of 1.71 eV, and under the illumination at 25 degrees, you can see that there's a highest PL peak appears at here, and as we've seen before, they sort of separates into iodine and wide band gap and narrow band gap regions. So we see two there are two now peaks here, and when we just suddenly elevate the temperature up to 80 degrees, you can see that the PL peak, that phase segregation sort of suppresses. And when we when we cool down the temperature below to up to 25 degrees, the phase segregation appears again. So it's clearly showing that the phase segregation is temperature dependent process. He proposed that there is a light induced strain and thermal disorder induced strain playing together. So at this region, we can clearly see that excess carrier density is reduced, as well as your lifetime. And also this is what happens under the illumination. The material is undergoing on a very large micro strain compared to the case in the dark. So you can see that with illumination, the micro strain is higher compared to without illumination under higher temperature. So these two, one is the light-induced strain, which is caused from the excess carrier reduction, and thermal disorder-induced strain is caused from the structural distortion. So they both reduces the excess carrier density. So if you have a less excess carrier density, that can suppress the phase segregation, because that sort of suppresses and reduces the polaron generation across your surface of the film. So that's one of the main reasons and for suppressing the phase segregation in your material. He also proposed a way to sort of suppress the phase segregation, and he put 15% of bromide and fabricated 1.67 EV wide bandgap halide perovskite solar cells, and he employed FABR and 2-pack material on top of your perovskite surface in order to cure the surface defects and improve the balance between the band energy levels between whole transport layer and your perovskite material. So once he treat the surface with these materials, so that's the control sample, and so he measured PL up to 300 seconds. You can see that the PL peak shifts and it will eventually have a split like we've seen before. If you put optimum amount of the FABR and 2-pack, you can see that this sort of shift in PL is suppressed, and we can put even more 2-pack material, but this sort of doesn't help much in terms of phase segregation. And we performed Kelvin Pro-Force microscopy on these materials, and this is 0%, so this is control sample, and this is one with, we only put 2-pack material, and this is mixed between FABR and 2-pack. We've seen that there's a homogeneous distribution in the work function. So this sort of passivation allows you to have a good bending between your materials, and also such uniform work function prevents the carrier funneling between nanoscale regions. So that sort of suppresses and helps the phase segregation. And another student, Minu, has also fabricated wide band gap up to 1.75 eV. So he put quite a lot of amount of the 40% bromide. And like we've seen before, if you put more bromide, you will eventually have more phase segregation and more disorder in your film. However, he treated film surface using long chain cation iodide. So this is so-called PAI. And this PAI helps you to form more P-type nature on top of your surface. And eventually it will help to extract holes. And he has achieved around, around 13% with 1.75 EV after treating the sample with PAI. And we've also seen a similar effect before, where if you perform PAI passivation, you will have more uniform distribution of your work function in nanoscale. And under the illumination, which is very consistent, that the distribution of the carrier is quite uniform, whereas your reference sample will have very non-uniform nature of the carrier generation. So he tested his sample up to 60 seconds and found out that they are very stable compared and having a higher voltage due to more efficient extraction of the carriers. So my other student, Hong Jae, he mainly works on nanoscale characterization, and we have collaborated with Chungnam National University. So they were able to form a very nice wide-banded perovskite using thermal compression bonding method. So what they did is they actually made two perovskites separately, and they bond the perovskites and gave a pressure with a temperature. And this method will eventually make a very good bonding between materials, and we'll have a transparent transparent perovskites, because you can have two glasses with a substrate and they just bind it together. So they achieved around 17%, but there's a bit of hysteresis, which we think there is still a lot of sort of defects in the bulk. And they were able to grow the crystal, sort of recrystallize the perovskites when they bond and press and make a denser interface. We performed the KPFM under the dark and under the light in order to see if there's any phase segregation effect. And we scanned the KPFM with the light on and off. So that's the control sample. And you can see when the light is on, there's some regions with different work functions starting to happen. And even we turn off the light, those regions remain the same. So there is going to be a very non-uniform distribution of the work function and charge generation, whereas your laminated sample, so one that got bonded, has a very stable and uniform work function and charge generation. And this sample shows very high stability, so eventually they are binded together, and they call it as a self-encapsulation. And under the 1.5 G, so one sun illumination, in air, the stability can be maintained up to 600 hours and only 5% of the degradation. I've got like 5-10 minutes. So lastly, I will talk about stability of the perovskites. So that's I'm going to focus mainly on the light-induced degradation. So if you encapsulate your material, it will eventually have less effect of the humidity. So, but there is always going to be light-induced degradation. In halide perovskites, there are many different mechanisms under the light illumination. Here I want to point out that there are two main effects related to carrier generation and degradation. So with your hole, it will be merged with the iodine vacancies, and there are going to be these species form and eventually evaporates. And if your material evaporates, escape out of your material, the structure will eventually collapse. And if you have electrons, we will interact with lead and form a lead zero, and this is going to make a very detrimental effect for recombination. So in order to improve your stability, it is very important that you extract your carrier efficiently, especially at the interface. So Eun-young is my former PhD student. She's now a postdoc in Diamond Light Source in Cambridge. And before she just left, this has been published and selected as a cover page in Advanced Energy Materials. So we worked together with KRICT, where they can fabricate very high efficient perovskite solar cells, and we also collaborate with University of Cambridge to study the degradation mechanisms. So that's the perovskite structure. So you have titania underneath the FAPBI3 perovskite, and this long chain iodide is deposited in a very thin way, so around 20 nanometers to surface to passivate the surface defects. And we employed aluminum deposited allox, which is a very convenient way to suppress the sort of evaporation of your halides and ions. And this is known to be effective especially for stability reasons. What we found is that when you have aluminum oxide onto your film, and if you anneal this film or if you illuminate light, your aluminum actually will diffuse into your perovskites. And what we found that once aluminum diffuses into your material, it actually heals, cures the defects in the bulk. And it also going to improve the stability quite a lot. So if you see the control sample, so that's under the continuous light illumination in nitrogen environment. You can see that control sample has around 20% degradation. When you have this passivation layer, it slightly increases your efficiency. However, you can see that the efficiency, the stability got worse. The main reason is that this long chain cation just evaporates quickly under the light illumination, as well as this halide. So if you have aluminum oxide on top of this material, so when they are sitting on top, you can see that, so that's the OAI O'Neill sample and OAI with allox sample. So we studied this using GI wax and found out that, so for control sample, there are going to be a lot of delta phase and loss of the A site cations, and having that results in lead iodide phase. The same case happens with OAI. However, you can see that with OAI and aluminum oxide, continuous illumination actually forms a very nice 2D layer on top of your perovskite. So this is the schematic, what happens under continuous illumination. So with O'Neill OAI, you can see that continuous illumination induces the evaporation of the iodines and OA cations. So the material just evaporates and we lose this material and collapse the structure. However, if you have aluminum oxide, we sort of suppress the loss of the volatile species and sort of traps these ions. And that ions under continuous illumination will self-form a 2D layer. So that's the 2D layer here, which is formed at the very top surface and also some in the bulk as well. So those 2D layer is hydrophobic and will definitely enlarge the stability because it will make the suppression of the volatile species to evaporate. We also did some stability studies with UNIST, and they employed a P3ST and nickel PC. So their performance, this sort of P-type layer has a very high thermal stability compared to conventional spiral material. So they tested this material under 40% humidity and 85 degrees without encapsulation, and you can see that it still can have a very high stability, and under the illumination as well. And under 85 degrees, 85 humidity, when it's encapsulated, and 1,000 hours can be maintained with only loss of efficiency around 20%. So Jihu has performed cross-sectional KPFM, and we found that there are going to be a strong electric field formed because of this Hall transport layer. So you can see that there is a large shift in the electric field difference, and under the light illumination, such electric field will eventually help the carriers to extract efficiently. So this is summary of my presentation today. So I hope you to remember a few things. I don't expect too much to be remembered, but these are very important concepts and topics I think is very relevant to, especially for halide perovskite and tandem solar cells. So if you mix iodine and bromide, you will obviously see a large VOC deficit. So as your band gap increases, you will have a lot of problems, but there are ways to suppress such problems, and I think there have been many good progresses. And this halide segregation, phase segregation, can be suppressed under 80 degrees. And also there are many ways to passivate the surface to suppress the halide segregation, and aluminum oxide can be used to improve stability. And we have a very good cross-sectional KPFM techniques to observe what happens at the interface. So you can also study degradation mechanism at the interface using cross-sectional KPFM. So that's my last slide. So thank you for listening. And we have, thanks to my funding bodies and my students. So that's all. Thank you.
That's great for a nice talk. We can take a few questions from the audience. Yeah, Tina? Yeah, wait for Rob.
Hi, this is Xiaojing from Surrey. Very nice presentation, and particular in terms of like phase segregation and also the stability issue. I think that's critically important for the perovskite field. One question you mentioned about like for the bromide one, when increasing the concentration of bromide in the perovskite, you see like more severe phase segregation. And also you point out at currently 5% seems okay. But I just want to ask a question because I believe all the characterization was done at room temperature or around 30 degrees. So I just wondering, for the 5%, like the bromide, if you apply 85 degrees, do you think this one need to be further reduced, or we need to have bromide-free perovskite?
I think ideally having 0% bromide would be good, but we can't enlarge the band gap. So eventually we will need to have bromide in some sense. But for instance, if we don't have bromide, I believe there isn't going to be much phase segregation. So 5%, from my results, there isn't much phase segregation, and it's sort of enough range in terms of phase segregation and stability.
Have we checked like the characterization at 85 degrees?
85 degrees, no, we haven't checked that one. We only checked the wide band gap perovskites.
Yeah, at the room temperature, right?
At room temperature, yeah.
Do we have the capability of checking that at 85 degree for the characterization?
Yes, we can. Yes, we can. Like nursery-tan, or we can even try high temperature using KPFM to check the phase segregation.
What about the nano IR?
Nano IR, I think it will be quite hard because the temperature will give a sort of fluctuation at the tip surface, so it will be hard to measure.
Okay, thank you. Thanks.
Thanks, Jay. Any other question? Actually, I'm interested in the fabrication process using the thermal compression. You calibrate with the Korea University. How do you make that like a perovskite absorber? You said you have two parts. Each part has perovskite absorber, and then you compress them together. So can you control the quality of the film as you using like solution method or other methods? Because the two perovskite are already formed, and then you like kind of compress them together. Do you have like interface between these two layers?
There is. You can, if you see cross section, there is. You can see there's an interface. However, Halide perovskite, the ions move very actively.
Okay.
So they form sort of a one layer instead of two separate layers. So I think it can be work if your material has very high crystallization rate, growth rate, and halide migration.
Okay.
Yeah.
If no other question, we thank the speaker again. Thanks for your nice talk.
Thank you.